Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here as a video number 2 here in a series about how to draw free body diagrams. So we're going to talk about this situation right here where we got these 3 boxes that I've labeled A, B, and C. And we're going to imagine this video here that they all have equal masses at 25 kilograms. And this person here walks up, pushes on these boxes with a force of 200 newtons, and we observe a 1 meter per second acceleration to the right. Now this video is going to be a conceptual, qualitative video. There's not going to be any math attached to it. It's going to all be about just how to draw the free bodies. But there are reasons why I'm putting some numbers to this for us to discuss. So the first thing to realize is what your free body looks like depends entirely on how you define your system, or sometimes it's called your system of interest. And there's lots of different free bodies I could draw, even with relation to just these boxes, right? One possible system of interest is the entire deal. And we'll go ahead and do that here in a minute. But before I do that, I want to talk about all the different possible systems here we could draw. So there's one. We could draw a free body of this entire system. Other possible free bodies. We could draw a free body of maybe only mass A. Or A and B together as a system. Or maybe just mass C. Or maybe mass B and C together. I don't know if I did it or not, but just mass B or just mass A. There's lots of different types of free bodies we can draw. I'm going to go ahead and draw. I'm going to consider the system of interest the entire kit and caboodle here, the whole thing. Now, when you draw a free body, really what you should do, I like to keep my original picture kind of clean, and you normally kind of clone the system here. It's easy for me to do in this computer system. Copy, paste. And we put that somewhere else. Now, I don't mean that this has moved over to the right. This is just a picture I'm going to put of my system here. And now I'm going to start drawing force vectors. Now, first of all, let's talk about the MGs here. You could put 3 individual force vectors, or what I'm going to do here is I'm just going to put one gravitational force down equal to mg. Where in this example, that m would be 75 kilograms, because that's the single force vector representing the total mass of the system. Right? There's also normals. There's force interactions along this surface, and this surface. Right? So in this picture, those forces would go along here, here, and here. They're upward on these objects. I'm going to go ahead and group those together, call them one force upward. Oops, there we go. I'm just going to call it N. And again, that's the sum of the normal force upward acting on A, the normal force upward acting on B, and the normal force upward acting on C. You don't normally, when you draw a free body, have to write all of this out. Usually whoever's looking at your work will understand that. All right, this person here is applying a 200 Newton force to the right. So we need a force vector for that. Oops. That force is applied. Now look at the contact point here. That force is applied right along here. So when I draw that force vector, I don't really have a choice up or down where to put that force vector. It is applied at that point. I do have a choice left or right. I could draw it here, or maybe here, or here. Again, force vectors have what's called a line of action. I'm going to go ahead and put 200 newtons. You could also just put F here. I've defined what that force is. Either one would be just fine. Now, whether or not there's other forces involved, that's kind of a case-by-case scenario here. When you have surfaces in contact like this right here, you have 2 possibilities. Right? You have normal force possibilities, and those will be there. But you also have a tangential force possibility. The tangential force is what we call frictional force. So one of the things you have to learn how to do in free bodies is decide, when is that frictional force relevant? So a lot of times there'll be wording in problems like, hey, make sure you include friction, or no, we're going to assume as a low friction or frictionless surface. This one I threw some numbers in to help us decide whether or not we should include a frictional force in our free body. Remember Newton's second law is net force equals ma. And these two forces are definitely going to add to 0 because this thing for sure is not accelerating up. If this were the net force, we'd have 200 newtons equals mass 75 kilograms times the acceleration, because the entire system here has a mass of 25 plus 25 plus 25. If you were to solve this for the acceleration, you're going to get a number bigger than 2. Okay, it doesn't matter what the actual value is, but when you take 200 divided by 75, you're definitely going to get a number larger than 2. But the observed acceleration in this example was only 1 meter per second per second. So what that tells us is there must be another force in this problem. So we're going to get rid of this. And that force, all right, this is the only contact point. You know, this stuff right here is the only contact where that force could be occurring. That force must be left, right? And that's an example of a frictional force. And really, in reality, this would be the sum of 3 other little frictional forces. The frictional force acting on A, like how much is along this surface, plus the frictional force acting along this surface, plus the frictional force acting along C. And again, normally when you draw free bodies, we don't normally write this stuff out. I'm just writing it out for examples. All right. Now, the point of this video is just how to draw the free bodies. I'm not going to bother with writing the Newton's second law equations, other than that one little example I talked about, the point of which was, you know, to help know why did we need a frictional force in this example. All right, so here's one free body for one possible free body for this. Let's go ahead and draw another one here. Let's draw a free body of just mass A. What would that look like? So what you do is you, again, the word I like is clone it, right? You would draw another picture of this somewhere. I'm going to go ahead and do that over here. Now we start putting force vectors in. Oops. I like to take my time and have these force vectors nice and straight. All right, we got a gravitational force. That's going to be down, acting at the center of gravity, which for most objects is pretty close to the geometric center. Good enough for this video. Got a gravitational force down, mg. Now this mass right here, that would just be the 25 kilograms. In going back to this free body, in fact, there's a good point. I can't call these just both m, because over here I've got mass A equals mass B equals mass C. This mass right here is the sum of the 3, 75 kilograms. In this free body, this is only of mass A, so I only want 25 kilograms. I think we better put a little A on there. Call it m sub A g. Good enough. Oh, let's make that a little easier to read. M sub A times g for that force vector. Now, contact points, right? Again, on mass A, there's a contact right here again. That's going to give us a vertical normal. We'll call that, how about we call that normal A? That's the normal which is upward on this surface, on this object. That same normal acts downward on this surface, but the free body is a free body of the box, so we want the vertical one. Okay. Contact point right there. So we need to put a force vector for that. That 200 newtons acts to the right. Whoops. Drawing force vectors in black. Let's be consistent with that. We could label it either F or 200 newtons because I've defined them both. They're equal. Vertically, we want to put it where the contact is. We don't get freedom there. You do have freedom right or left. I could draw it over to the right if I wished. Now, this free body is not yet complete. There's a couple things to consider. Here's another contact point right here, right along there. That's going to create another force that we would typically call a normal. That force would be to the right on this object, left on mass A. It's important to realize that contact force between these two is what's accelerating this part of the system. That normal, I'm just going to put it at the geometric center. I know that that normal here has to be less than this because this thing is accelerating to the right. And let's see, that's the normal between A and B, so why don't we call that normal AB or something. Another possible force vector, right? Remember, we put a frictional force on the whole thing. Some of that frictional force acts along this surface. So we have a frictional force left. Oops. and that frictional force is the frictional force acting only on A. And I think that's pretty well good enough for that free body. I'm going to go ahead and draw one more. I'm at 10 minutes here. I don't like these to get too long. And I'm going to do this one kind of quick. Let's try drawing a free body of this part of the system right here now. We're going to define our system as B and C. Copy, paste. Okay. And I'm going to do this one a little quicker, trying to keep this video here short. And again, if you're somebody who you're right now just learning how to draw free bodies, what I would do is I would pause this at this point and see if you can draw the free body of this system, and then check it against what I do next here. So I would go ahead and do that. All right. I'm going to go ahead and draw my free body now. Oops, what am I looking here? Oh, there we go. First force vector I would put is the gravitational force vector, mg. One thing I've not done in this video that I probably should have is paid attention to relative magnitudes here. Remember, this mg here was all of it. This was just one of it. Should have probably drawn that one a little shorter. I'm going to go ahead and leave this to this length. This one is at least larger, but this vector here should actually be 3 times larger than this one and twice this one, but we don't need to be that detailed in this picture. This m would be mass A and mass B. Right, 2 normals upward. Right, so this one would actually equal normal on A plus normal on B. Now, acting to the right, we got several things acting to the right here. Now, remember this normal that we put to the left on mass A? That same normal acts to the right here on mass B, so normal AB. These would get the same label because they're the same force. That's a force pair. That's a pair of forces, all right, interacting between these surfaces, left on this mass, right on this mass. Now, here's a surface in contact. This, if we put a normal there for BC, that force would be right on C, left on B, but they numerically add to 0. That's an example of what we call internal forces. Internal forces usually do not go in free bodies, so we don't need to put a force vector there for the interaction between these surfaces. And then we've got frictional forces acting along these surfaces. Those force vectors will be to the left. That's the friction acting on B and C together. If I actually relate it back here, it's the sum of these two. And I think that's it. So the video's at 13 minutes. I'm going to go ahead and leave it there instead of doing more examples. Other free bodies we could draw. We could, draw this system. We could draw just mass C. I'm going to go ahead and leave this alone, though. That's probably enough. Some things I didn't do in this video. I didn't pay a lot of attention to the relative magnitudes of these force vectors. I probably should have, but at least in my free body, like here, I know that the net force is to the right. You'll notice I at least drew the 200, less than this guy. Same thing over here. If you look horizontally, this 200 should be longer than the sum of these two. And over here, net acceleration is to the right, so this one's got to be larger than this one. I'm going to go ahead and at least change that. We'll shorten up the other one. Now this is getting to be a little more detailed than you need for most free bodies. Generally speaking, if you at least get them in the correct directions and labeled correctly, that's usually good enough to move forward and use the free bodies for what they're meant to be used for, which is writing Newton's second law equations. And also I use them a lot for evaluating work terms when you're looking at principles of work and energy. So anyway, this is just meant to be video number 2 in a 2-part series here on how to draw free body diagrams. I hope that this has helped. Have a great day.